Hello children, how are you all? Hope you all are fine and doing well. My name is Naresh, welcome to our channel Physics Plaza. Children, we are doing the work power energy series. In a last class, we discussed about what is a work and when the work done is positive, when the work done is negative, when it will be zero. Then we discussed about the SI units of work done and the Cgs units of work done. Children, when you can see that work is done? The work is said to be done when the force acting on the body should displace. But here we cannot say that every time body can be displaced in the direction of applied force. So in that case we will get actually W is equal to Fs cos theta. Children, F is a magnitude of force, S is a magnitude of displacement. What is theta? Theta is a angle between force and displacement. So here what happens if if the body is displaced in the direction of applied force, then theta will be 0. So cos 0 will be 1. So W is equal to Fs. That is, work done is positive. When the body is displaced in the direction of applied force, work done is positive. And in some cases what happens, body may not be displaced in the direction of force, rather it may be displaced opposite the direction of the force. The best example, as I can throw this marker vertical upwards like this. So the body is going vertical upwards, but the gravity is acting downward direction. So in that case, theta will be 180 degrees. Cos 180 will be minus 1. So W is equal to minus 1 into Fs. That will be minus Fs. So work done is negative. If the theta is 90 degrees, that is what? When the body displacement and the force both are like perpendicular to each other, then theta is equal to 90 degrees. That is, cos 90 will be 0. So Fs into 0 will be 0 only. So then work done is 0, we can say that. But dear children, when a body is like moving in a circular path, let us say that to horizontal plane. How? Let us take this marker. It is going like this, circular path. Just imagine the circular path, not like this. This called as a vertical it is. So like this, vertical path like this. The body is going in a circular path, that to horizontal plane. Horizontal plane it is going like this. Then what is the work done in that case? How can we calculate the work done? Then what can we say? The body is moving in a circular path, that to in a horizontal plane. Okay. Let us imagine here is a horizontal plane. Here is horizontal plane. Okay. And let us say here center. Here is, let us say, here is an object. It is an object. So dear children, as we know that the body which in a circular path, the body which is moving in a circular path, especially in a horizontal like a plane like this, the continuous force will be acting on the body, which always try to pull the body towards the center, is called actually centripetal force we discuss. Of course, here is centripetal force, centrifugal force. Again, that is a complete different discussion. So let us take what is the force acting on this body which is a circular path. Definitely we can say it is a centripetal force. Let us take it as a centripetal force. So this is what actually the direction of centripetal force towards the center, let us say, towards the center. Then what is the work done by this centripetal force on this body which is going in a circular path in a horizontal plane. Children, if you want to know the work done by the force, and we should know that in which direction the body is displaced. Children, the body which is in a circular path, at every point, the displacement will be along the tangent like this. The displacement direction will be always like this only. So this is what actually displacement direction. So it is a force direction. Now what is the work done by this centripetal force on this body? So look at here. Centripetal force is towards center, displacement is along the tangent. Now look at here, what is the angle between these two, children? So the angle between centripetal force and displacement is 90 degrees. It is 90 degrees. So we know that W is equal to here Fs cos theta, and theta is equal to how much? It is a 90 degrees. So it will be Fs cos 90 degrees. Children, cos 90 is equal to how much? Cos 90, 0. So 0 into something will be 0 only. So here W is equal to 0. Which means what, dear children? The work done by the centripetal force, in this case, it is 0. Children, as a work done by the centripetal force, or else no work is done on this body. As no work is on this body, there is no change in speed. There is no change in speed. As there is no change in speed, its energy also remains constant. There is no change in kinetic energy because it is going with a constant speed, constant. Here 20 meter per second, 20 meter per second, 20 meter per second, 20 meter per 20 meter per second. Why it is going with a uniform speed? Because no work is done on the body. As no work is done on the body, there is no change in speed. As there is no change in speed, there is no change in kinetic energy. So it is moving with a constant energy. So this is what actually the work done on the body which is in a circular path. Work done by the gravitational force. So let us see. Suppose here is a body of mass m. Body of mass m. Okay, children, is placed. Let us say it is placed at a certain height of h. It is a place at a certain height of h. So when it is left, what will happen? Definitely, it falls freely. And don't you think that there will be gravitational force acting on this body continuously? Of course, it is acting. Gravitational force acting. So what is the direction of gravitational force? Gravitational force will be acting downward direction. That is F. Let us say F. So what will be the displacement of the body? Body also displaces vertically downwards. No doubt about it. This is a displacement. Now, as force is acting and there is a displacement, and that too both are in the same direction, that is parallel. So definitely there is a work done. Then how to calculate the work done by this gravitational force on this body? Children, what is the work formula? W is equal to here Fs. Children, why I am taking Fs? Why not Fs cos theta? Anyhow, here body is displaced in the direction of force. Children, whenever body is displaced in the direction of force, let us take W is equal to Fs. Anyhow, theta is going to be 0. So cos 0 is 1 only. So you will get finally W is equal to Fs only. So, but here very important thing is that, okay, S means this vertical height will be S. This vertical height actually. So H is going to be the displacement. Then how to calculate the F? Children, here if you can think about that, due to the gravitational force only, body possesses what? Weight actually. What is weight? Weight is nothing but the force with which body is pulled by the gravity. So that is what? Weight is nothing but the force with which object is pulled by the gravity. But W is equal to what? We know that weight, that is the mass into acceleration due to gravity. So here in the place of F, what we can add directly? We can add mg. So here mg into S is what here? H. So finally we got W is equal to mgh. So children, this is the work done by the gravitational force. But here what is happening? The body is coming vertically downwards. As the body is coming vertically downwards, W is equal to mgh. Then what happens? What is the work done by the gravitational force when the body is thrown like this? A body is thrown vertically upwards. As the body is going vertically upwards, then what is the work done, dear children? There we need to think about the direction of the body. Means that is what, in which direction the body is displaced. Children, as in this case, as the body is coming down like a freely falling, the work done is positive. Why? The body is displaced in the direction of force only. If not, what happens? For suppose children, here is, let us say body is thrown vertical upwards so that it has a certain height. Let us say it is a h. H is a displacement. But the body is displaced vertical upwards. Don't forget that. And the force of gravity is acting vertical downwards. Magnitude will be same. Because the force of gravity on the same body, because we are not changing the mass. So W will be mg only. But here in this case, W is equal to Fs cos theta. Here theta is going to be 180 degrees. Why? Body is displaced vertically upwards. The force of gravity is acting downward direction. So it will be -1. So then Fs into -1 will be W is equal to minus Fs. So minus Fs. So in the place of F, what we should take? Mg. Mg we should take. So we will get minus Mg. In the place of S, we will take a H. That will be Mgh. So children, magnitude is same whether it is going vertically upwards or downwards. For a given height, for a given mass, the work done is same only. But difference is that, so when the body is coming vertically downward direction, the work done is positive, whereas when the body is thrown vertically upwards, the work done with the force of gravity is taken as a negative. So this is how actually we can calculate. Children, now we will see actually how can we calculate the work done with the help of actually force and displacement graph. But before that day, children, do you think that always the same constant force acting on the body in our daily life actually? In fact, it is not that actually. In our daily life, we cannot say that always the force acting like a constant amount only. But let us assume that the force acting on the body is a constant. Let us suppose 10 newtons force. Continuously, 10 newtons force of 10 newtons of magnitude of force is acting on the body continuously, so that body is displaced. Means at every time, for example, it is a body. Let us take here is a body. Here is a body. So it is what is happening? 10 Newton only. 10 Newton, 10 Newton, 10 Newton, 10 Newton. Means every second, at every point of time, the force acting on the body, let us say 10 Newtons only. So that the body is displaced. The body will have different displacements. So in that case, if we can plot a graph of force versus displacement, how the graph will be, let us take. So children, as I told you that for a constant example, we are taking F is equal to 10 Newton. Example, it might be anything actually. It is not compulsory that only 10 Newtons. But what about displacement? Displacement might be like a 2 meter, 4 meter, 6 meter, something different displacements there. In that case, if you will plot a graph, look at here. So here is x-axis and here is y-axis. X-axis and here is the y-axis. And here on x-axis, here is a displacement is taken, and x-axis here is displacement. The y-axis a force is taken. So force is taken in Newton, displacement is taken in meter. So for suppose here is 0, 20 Newton is like this. So if you can sketch a graph for this. So initially when the force is acting, let us say initially there is no displacement. Initially let us say displacement is 0. So this point, so though the force is acting, there is no displacement. So let us say this is the point which you will get here. And for the same 10 Newtons force, displacement is 2 meters. Next 4 meters. So like this, if you will make the children, so we will get all dots like this. All dots like this. So connect like this. So we are getting straight line. We are getting a straight line parallel to the x-axis. So dear children, so when the magnitude of force acting on the body is a constant, and but body will have a different displacements. Then when we can plot a graph like force versus displacement, so we will get a straight line. Why straight line? The force is a constant, but the body has a displacement. Different displacement. But in this case, how to calculate the work done? How to calculate the work done? So just look at here. Let us say it is a O, or else it is A, B, C. So look at here. So can we say it is a D? Yes. Here you can see like one rectangle shape we got. Rectangle shape. So the area, the area enclosed by this BC, the area enclosed by this will give you actually the work done area. So how to calculate the area enclosed by this? The area enclosed between BC line and the displacement axis. So how to calculate here? We know that area is equal to children. So how to calculate the area of this rectangle? It is a BA into BC. That is BA into BC. So BA is what actually? BA is what actually here? It is on BA. It means y-axis. What is taken? Force is taken. So that is force into, and what? BC. So BC is a parallel to AD only, right? AD only. So it is taken on x-axis. What is taken? Displacement. So F into S. So F into S, sorry, it's a work done. So force into displacement. So the area enclosed by this area, what are this shape? Let us say the area under this BC and AX will give you W is equal to actually Fs. W is equal to Fs. So if you want to calculate in this case work done actually, you know, so AB is equal, BA is equal to how much? It is a 10, and here AC is equal to how much? It is 8. So it is 80 joule. This is how actually we can calculate the work done by the constant force. Work done by the constant force. But actually in our daily life, you know, in daily life, this is not a situation what we find actually. Mostly, you know, though we apply the force continuously, so we are not sure that only always 10 newtons of force will be acting. Children, we are not a machine. For every second to measure 20 newton next, 20 newton next. It is not that. So what is the force which we are applying may differ. So definitely the force acting on the body is a different, means definitely body also may have different displacements. For example, children, I am saying, the force acting on the body, let us say, for example, you know, like 2 Newton, 4 Newton, 6 Newton, means the magnitude is changing continuously. Then obviously the displacement also changes. Let us say it's like, you know, 2 meter, 4 meter, 6 meter. Actually, where I am taking a special case, where exactly displacement is a proportion to the force. Actually, let us take it as one more case. Of course, in our daily life, it also may not happen, children. Exactly, we cannot say that. Exactly, 2 Newton force, 2 meter displacement. 4 Newton force, 4 meter. Of course, we are not sure that. Actually. So here, I want to take a case where the force is not a constant actually. So in this case, actually, if you can plot a graph actually, so how we will get, let us see here. So here, children, let us take, here is x-axis and here is y-axis. So as usual like this only, and x-axis displacement in meters it is taken. Whereas on a y-axis, force is taken in a Newton. So then as I told you that the situation where the force acting on the body is continuously increasing, at the same time the displacement also increases proportionally. I am saying proportionally. Then we will get a straight line like this. We will get a straight line which is passing through the origin. But in this case, how can we calculate the work done? Simple, same thing, teacher, same way. The area enclosed, for example, let us say it is a OA graph, let us say. So on this we have taken 2 meter, like a 4 meter, something like this, 6 meter, it is 8 meter, let us suppose. So this will be 5 Newton, 10 Newton, something like it is a 50 Newtons we have taken. So now the area enclosed, this one, between OA and this OS will give actually this work done. So now what is the shape of this one? Is like a triangle, you know. Now we need to calculate the area of the triangle. The area of the triangle will give you work done. So let us calculate this area. So this area of the triangle will give actually it is a work done. So is equal to half into. So this is what is, children? Base. So let us say OAB. So this is OB into BA. So this you will get 1 by 2 into OB is how much, dear children? 6. And BA is how much? It is 15. So BA is equal to 15. So this will be 15. So 2 1s are 2 3s. So it is 45 joules. 45 joules. So children, this is how actually we can calculate the work done. But you may ask one question, sir, in our daily life, do we expect that always the displacement, the force, both are like, you know, proportional to each other, like perfect, like a 2 Newton force, 2 Newton displacement, 2 meter displacement, 4 Newton's force, 4 meter displacement? Actually, it is not that actually. It is not that. But you know, in a day-to-day life, if you can take on a daily life situation and if you can plot a graph, how we'll get, you know, we may get like this actually. So here is displacement and here what a force. So it is not compulsory to get always straight line only, children. It's not that. Maybe like this also. You may get. We may get. It's not a compulsory that always to get straight line only. So in that case also, we have to calculate the area enclosed by this curve and the displacement axis will give you. But for this, we may not follow this regular method. Rather, we'll follow the integration method that will be learning in a further classes. So this is how actually we can calculate the work done by the constant force and a variable force. We will discuss about power. Children, what is the power actually?
You know, in a day-to-day life also, when small children are playing, they'll be talking, hey, I have more power than you, Ray. Means like that actually. But what does it mean actually, power? In our day-to-day life actually, where we can use this concept of power, when you can say that one person is more powerful than other person. Let us see, for suppose, let us take here is one person, let us say person A, and here is person B. Two persons are there, two persons, and the same work is given, same task is given to this person, person A and person B. Same task, let us say some work, same work is given to lift something or to run somewhere or to carry something like that. Those kind of work is assigned actually. So if let us say TA is a time taken by a person A to complete the work, whereas TB is a time taken by the person B to complete the work. If TA is greater than TB, look at here, children, don't get confused. Which means what? Person A is taking more time than that of the person B to complete the same work. Children, then who is completing the work early here? Person B. Person B is completing the given work in a less time. But whereas person A is doing the same work, but it's taking more time. So here, then we can say that person B is more powerful than person A. How can we say that? Yes, we can say the rate of work done. The rate of work done means person B is taking the less time to complete the same work. So what is power? The power we can measure in terms of work done with respect to time. So mathematically we can say power is equal to work by time. Power is equal to work by time. Also we can say the rate of doing work. The rate of doing work is called power. Children, as means for a given work, power is inversely proportional to time. That is, power is inversely proportional to time. So for same work, if a particular person is taking less time, which means what? The person is said to be having more work, more power. If the person is taking more time, which means what? The person is having less power. So power is what? The rate of doing work is called power. Rate of doing work is called power. Children, as we know that W is equal to F dot S. Already we discussed in the previous sessions. So work is the dot product of force and displacement. So in the place of W, now let us substitute F dot S. So what can we get? P is equal to F dot S by T. Children, can I write like this one? F dot S by T. Of course we can write, but what is this which is written in the bracket? Displacement by time. Children, what is the displacement by time? Come on, tell me. Displacement by time is called what, children? Velocity. So this we can write the velocity. So power also can be written as the dot product of force and velocity. It's very, very, very important. So children, as I told you, it is one of the properties of dot product. The dot product of two vectors is always a scalar only. It's always scalar only. So power also scalar as like a work. Now let us see the units. So what are its units? So first let us see the SI units. Children, in SI system, work is measured in joules. Whereas time is measured in seconds. So power is measured as joule per second. Children, this joule per second only, we can call it as a watt. W-A-T-T, watt. So representation is capital W. Children, whenever you are writing complete name of the unit, so first letter should be small letter. It's very, very important. So watt is the unit of power. It is also called as joule per second. But children, whenever we are dealing with a more power, especially mechanical engineering, or else whenever you are talking about the power of some vehicles, what will become very small unit. There will use actually the unit called horsepower. Children, the practical unit of power is a horsepower. So here horsepower, 1 horsepower is equal to 746 watts. So it's very, very, very important. 1 horsepower is equal to 746 watts. 1 watt is equal to, we can write it is 1 by 746 horsepower. 746 horsepower. Let us multiply with 1000 both sides. So it will become 1000 watt is equal to 1000 by 746 horsepower. So therefore 1000 means what? Kilo. So here 1 kilowatt is equal to 1000 by 746. How much direction? It is 1.32 approximately. 1.32 horsepower. Children, this is how actually watt and horsepower are related. Now let us see the Cgs units. So what are the Cgs units of power and how Cgs units are related to the SI units? Look at here, Cgs units, let us see it, children. Cgs units. In the Cgs system, what are the units of work? Erg. And a time is measured in seconds only. As work is measured in erg, time is measured in seconds. So power is measured in erg per second. Erg per second. But how SI units of power are related to the Cgs units of power? Let us see, children. So 1 joule per second. 1 joule per second is equal to, children, we know very well what is that. 1 joule is equal to 10 power 7 erg. 10 power 7 erg. So now in the place of joule you can write 10 power 7 erg. So it will be 10 power 7 erg per second. That's it. So this is how SI units of power are related to the Cgs units of power. Okay, children, this is what actually power and its units. Children, now we will see energy. What is energy? How is it related? How is it related to the work done? How is it related to the work done? Children, actually, in fact, energy and work done both are relative terms. Both are relative terms. Which means what? If we have energy, which means we will be able to do some work. As we are doing work means what? We have some energy. We have some energy. Means energy is the ability to do the work, the capacity to do the work. For suppose one person has more energy, which means what? The particular person is able to do the more work. If a person is energyless, bit dull, so definitely he cannot do the much work. So energy will give you the information regarding whether a particular person will do more work or less work. So energy and work both are relative terms. Both are relative terms. Very, very, very important. Then what are the units of energy? Children, in a SI system, as like a work SI system, energy also measured in joules. Joule, joules. Symbol is capital J. Whereas in a CG system, it is measured in erg. It is measured in erg. And we know that 1 joule is equal to 10 power 7 erg. 10 power 7 erg. It's common only. But children, other than joule and erg, we have some other units for energy. Let us discuss what are the units other than joule and erg. It's very, very important. Let us see here. So the first one is actually, children, from the concept of work, we know that work and power. So power is equal to work by time. As power is equal to work by time, can I write like this? Work is equal to power into time. Of course, we can. So as I told you that this work indicates what actually? Energy, the amount of energy. So this I can write here. Energy is equal to power into time. Energy is equal to power into time. So power is measured in watt. Time is measured in seconds. But we cannot measure the what we can say power of a particular vehicle or a machine in 1 second. Minimum will measure in hours actually. So time we can take it as hours. Watt hour. Children, try to understand. So watt hour is a unit of energy. Try to understand. Don't get confused. Watt is a unit of power, but watt hour is a unit of what? Unit of energy. It's very important. So this is the first point which we should understand. And one more thing is that here watt is a unit of power, as I said. Even we also can express the power in terms of kilowatt. Kilowatt also we can measure. So then it will become kilowatt hour. Kilowatt hour. Children, try to understand here. If you express the power in terms of watt, in terms of watt, then watt hour will be the unit of energy only. Even you can express power in terms of kilowatt. So kilowatt hour also is unit of energy only. But what is watt hour? What is kilowatt hour? How can we define that? And how watt hour and kilowatt hour relate to the joule? It's very, very important. Let us see. For suppose, dear children, let us see watt hour. We'll discuss What is a watt hour? Let us take, here is a machine, particular machine. Its power is watt, 1 watt, let us say 1 watt. So definitely when this machine is operated, definitely it can spend some energy. So the energy spent by this machine, of power of 1 watt in 1 hour. Try to understand. If this particular machine is operated, what is the power of the particular machine? Watt, 1 watt. So how long it is operated? It is operated for 1 hour. So as a machine of power 1 watt is operated for 1 hour, definitely it can spend some energy. That energy spent only we can call it as a watt hour. So the energy spent by the machine of power 1 watt in 1 hour is called watt hour. So how watt hour is related to the joule? Let us see, children. So 1 watt hour is equal to how many joules? Let us see how many joules. So look at here. What is joule per second, and 1 hour is equal to 3600 seconds. 3600 seconds. Let us substitute here. So which is equal to 1 watt is joule per second, and 1 hour is equal to 3600 seconds. So it is 3600 seconds. So second gets cancelled. So it is a 3600 joules. Hope it's clear? Fine. Now let us see what is kilowatt hour. What is kilowatt hour? Simple thing, children. Very simple. Very simple. What is kilowatt hour? How can we define? So let us assume one machine. Children, it is a machine. Okay. Its power is kilowatt. So the machine with the power kilowatt, it is operated for 1 hour. As it is operated for 1 hour, definitely it spends some energy. That energy spent only we can call it as a kilowatt hour. I repeat once. The energy spent by the machine of power kilowatt in 1 hour. It's called actually kilowatt hour. Let us see now. 1 kilowatt hour is equal to how many joules? Children, it's very important. So 1 kilowatt hour is equal to how many joules? Children, kilo means what here? Kilo is 1000. Watt is equivalent to joule per second. And here hour, 1 hour is equivalent to 3600 seconds. Let us substitute. Very simple. In the place of kilo, just let us write 1000. In the place of watt, write joule per second. In the place of hour, you can write 3600 seconds. 3600 seconds. Look at here. Second gets cancelled. So here 1 kilowatt hour is equal to so 3600 into 1000 joules. So this how can we write it, children? So 2 zeros, 3 zeros. We can write 36 into 10 power 5 joules. But children, according to the order of magnitude, it can be written as 3.6 into 10 power 5 joules. So finally 1 kilowatt hour is equal to, we are getting 3.6 into 10 power 6 joules. That's it, children. So this is what 1 kilowatt. Children, how watt hour is related to joule? How kilowatt hour is related to the joule is very important. 1 watt hour is equal to 3600 joules. At the same time, 1 kilowatt hour is equal to 3.6 into 10 power 6 joules. Children, other than joule and earth, so watt hour is also unit of power, watt hour is also unit of energy only, and here kilowatt hour also unit of energy only. Now let us see what is a calorie. Children, already we have discussed in calorimetry that the Cgs unit of heat is what? Calorie. But heat is nothing but the energy only. So now we have to discuss the calorie. So calorie also unit of energy only. But what is calorie, children? Once again, just recall once which is discussed in calorimetry chapter. Children, here is 1 gram of water. Let us take 1 gram of water. Initially it is at 14.5 degrees Celsius. So if you want to raise a temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. Children, in order to raise the temperature from 14.5 degrees Celsius to 15.5 degrees Celsius, some amount of energy should be supplied, heat should be supplied. This energy only we can call it as a calorie. We can call it as calorie. Means the amount of heat energy required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius is called calorie. But how calorie is related to SI unit of energy? Children, 1 calorie is equal to 4.2 joules approximately, or 1 joule is equal to, it will be 0.24 calories. 0.24 calories. This is how calorie is related to joule and joule is related to calorie. And other than this calorie, we too have one more unit, that is called electron volt. But where we can use it, children? Children, when we want to measure the energy of the subatomic particles, actually, these all are become actual bigger units. So there we need to go for actually electron volt. What is electron volt? How is it related to the joule? Let us see once. Electron volt. Let us learn. Electron volt, we can write like a small e, capital V. What is electron volt? What is electron volt? Children, let us take here is electric field, where let us say the point A and point B, such a way that the potential difference is 1 volt, let us say, and here some charge or electron is there. When this electron is accelerated, to the electric field, definitely it can possess some energy. So the energy possessed by the electron or a charge, when it is accelerated through a potential difference of 1 volt is called electron volt. Children, what is the charge of the electron? The charge of the electron is 1.6 into 10 power minus 19 coulombs. Then you make it a wonder, sir, why are you not saying minus? Children, here I am talking about the magnitude. So magnitude of the charge of the electron is 1.6 into 10 power minus 19 coulombs. Let us see once. So here the charge of the electron is 1.6 into 10 power minus 19 coulombs. Okay, whereas then volt, children, volt is nothing but what? Joule per coulomb. Volt is joule per coulomb. Now let us see here. 1 electron volt equal to how many joules? 1 electron is equal to how many joules? So in the place of E, substitute 1.6 into 10 power minus 19 coulombs. That is 1.6 into 10 power minus 19 coulombs. Then volt can be written as joule per coulomb. Let us write here. It is joule per coulomb. So coulomb gets cancelled. So finally we have 1 electron volt is equal to 1.6 into 10 power minus 19 joule. So children, this is how electron volt is related to the joule. So children, this is what actually energy, and these are the units of energy. Now let us summarize the things what we have learnt. Children, here we discussed about power, we discussed about energy and units. Let us see once. So here is power. Let us talk about power here. So here, children, power is equal to, we got it is work by time. It also can be written as F dot S. So its SI units are joule per second. It only we can call it as a watt. Whereas its Cgs units are, erg per second. How these two are related? 1 joule per second is equal to 10 power 7 erg per second. And other than this, we have practical units of power are called horsepower. So 1 horsepower is equal to 746 watt, or 1 kilowatt is equal to 1.32 horsepower. Children, this is all about power. And comes to the energy. What is energy, dear children? The rate of doing work is called actual power. But what is energy? The ability, the capacity to do the work. More the energy, more is a ability to do the work actually. So here energy is almost talking about actually work only. So the SI units of energy are joule, Cgs units of energy or erg. Children, how joule and erg are related? 1 joule is equal to 10 power 7 erg. 1 joule is equal to 10 power 7 erg. So other than this, we have watt hour. Children, watt hour is a unit of energy only. So 1 watt hour is equal to 3600 joules. Next, we discuss about kilowatt hour. 1 kilowatt hour is equal to 3.6 into 10 power 6 joule. And next, we have a unit of energy, calorie. 1 calorie is equal to 4.2 joules. 4.2 joules. Next, finally, we discuss about electron volt. 1 electron volt is equal to 1.6 into 10 power minus 19 joules. So, children, these are the units of energy and how they are related to the joule. So, children, in our next upcoming session, we will be discussing about what is a mechanical energy. There, individual will discuss what is a kinetic energy, what is the potential energy. There, we are going to discuss about even law of conservation of energy. Okay, children, thank you so much for watching the video. All the very best.